Hey everyone, my name is Demir, and today I'm going to talk about a paper titled Opening the Black Box Automated Software Analysis for Algorithm Selection. And this work is done in collaboration with Maria Anastasio, her advisor, Holger Hus, as well as my advisor, Lars Karhoff. So first of all, what is algorithm selection and why should you care about it? This is a chart that I made from SAT Competition 2018, and each dot represents a problem instance, and the numbers represent the number of seconds. So 5,000 is a timeout limit, that's when the solver gets terminated, and diagonal line is a line of equal performance. On the x-axis, there's the winner of the competition, and the y-axis, there's the solver that performed the worst in the competition. So what you see is that in most cases, the winner of the competition performs way better than the solver that performed the worst. The solver that performs the worst times out on a lot of the problem instances. However, there are a couple of SAT instances where it's reversed, where the winner of the competition times out and the solver that performed the worst solves those specific problem instances within a couple of seconds. So automated algorithm selection addresses this issue by automatically selecting the most appropriate algorithm for each use case in order to solve all the problems more efficiently and utilize all of the algorithms to solve those problems efficiently. The way algorithm selection is done usually is by building models that take into account observed performance of each algorithm and features of problem instances, and then build one model per algorithm that predicts its performance. And once we have all of the performance predictions, we facilitate algorithm selection through that. One of the biggest issues with this approach is that algorithms are treated as black boxes. So we don't know much about them. The only thing we know about them is how they perform in practice. What we propose is to open up that black box and treat algorithms the same way that we treat problem instances. So the idea is to build one model that looks at the performance of all algorithms and the features of problem instances as well as the features of algorithms, to then perform performance prediction, and then through that algorithm selection. We evaluated our approach on 9 different datasets or scenarios. So most of these scenarios come from Boolean satisfiability domain, and the reason is because there's a lot of data on Boolean satisfiability competitions, so it's easily available. And also, scenarios that are starred are scenarios that we have to modify in some way. So sometimes solvers source code of solvers was not included, or it was not clear what version of a solver corresponds to the solver that was used in the competition. So we had to exclude some of the solvers in those starred scenarios, and we also had to create our own scenarios. So SAT 18, EXP, GlueHack 18, and MaxSat 19. So what are the algorithmic features that we extracted from algorithms? So we can divide them up into 2 main categories. The first one is based on code, and the second one is based on ASTs, or the abstract syntax trees. So the ones that are based on code are things like lines of code, cyclomatic complexity, number of files, whereas features that are based on abstract syntax trees are the features such as number of nodes, number of edges in ASP, what kind of nodes and edges are there in an AST. We also included a third feature set that we call dummy ID features, and what those are essentially IDs of algorithms, and they're encoded in one hot way, in a one hot encoding. And the idea of dummy features is that we wanted to see how much of a performance improvement that we observe with our experiments is due to the fact that we build one model per entire dataset or scenario, and have all of the algorithms together versus the fact that we extract interesting and meaningful algorithmic features. In order to move on to results, I first have to explain some of the terminology used in automated algorithm selection community. The first one is MCP, or misclassification penalty, and that is additional cost that you incur if you select not the most optimal algorithm. And the single best solver is the solver that is best on average. So this is what you would typically do if you didn't know about algorithm selection. So for example, in the case of set competition, that could be the winner of the competition. And the virtual best solver is the best possible solver chosen for each problem instance. So this gives us the upper bound for the best possible algorithm selection method, whereas the single best solver gives us the lower bound of algorithm selection. So we report our results in terms of the mean gap closed between the single best and the virtual best solver. So what that means is if a number is 0, that means that our algorithm selector performed as good as a single best solver. And if our number is 100, it means that we did the perfect algorithm selection, so we achieved the virtual best solver. So there are two main types of experiments that we did. The first one is based on regression models, and the second one is based on pairwise regression models. In the regression models, we predict the performance of algorithms, whereas in the pairwise regression, we predict the performance difference between algorithms and then aggregate that to perform algorithm selection. And I in each column stands for instance-only features. Double I is for instance and dummy ID features. IC is the instance and code features. IA is the instance and AST features. And ICA is all of the feature set, so instance, code, and ASTs. So what we see is that if we look at the MCP for regression models, we see that we perform better than our benchmark approach of just using instance features in 8 out of 9 cases. And when we look at the pairwise regression, we're looking at performance improvement in 6 out of 9 scenarios. We also perform experiments on algorithmic feature importance, and we refer you to look at the full paper because of the time constraints. So with our work, we demonstrate that we can improve algorithm selection by looking at, by taking into account algorithmic features that are easy to extract and easy to understand. And for the future work, we want to extend it into the kinds of scenarios where the performance metric is not runtime, but rather a solution quality. We also want to look into extending our approach into automated algorithm configuration, and also perform in-depth analysis of the relationship between algorithmic and instance features and how that relates to the overall performance of our new algorithm selectors. And if you're interested, please refer to the full paper for more details, and